Good afternoon. Nick said start with an elevator speech. I trained as an astrophysicist and then later as a solar physicist. Worked for the National Solar Observatory and then moved to NASA, where due to recent circumstances, many of you know about funding from the government. Well, I don't have NASA under there, so I retired so that perhaps some folks like you could still pursue the job. So I appreciate that. So today, the title is grandiose in the sense that we can't talk about everything you could do with photons from the EUV to the IR. I'm sure you can appreciate that. It's much too much. So let's first talk about what we can do. And even before that, thanks to organizers and people running this school, Lika, and of course NASA for its support, Farzad, Nick, and UCAR hosting us today, and all of you. All right, so goals. They can't go. It was like so many of these talks, it's a choice between breadth and depth and where to take that. So I decided to go into a couple of key topics, enough that you get the flavor for the physics behind it, so that if you decide to go in a region like that, you understand what's under the hood or the bonnet, so that when you're using complex software, as you will, or you will write, to at least have an appreciation of what the complexities are in implementing that and what its shortcomings might be. So I'll focus on magnetic fields and the distribution of temperature, mainly in the coronal plasma, because you're going to run across that, at least in solar physics, all the time. In terms of magnetic fields, of course, you've heard a lot in terms of also magnetospheric plasma and other, but I won't be focusing on that. So a long list of things that are missing, and I won't go through it all. But we will talk about magnetic fields a lot, but not about what in physics is considered strong magnetic fields, which is defined at its behavior in the atom. We rarely see that, if ever, on the sun or in any heliophysical environment, so I won't talk about it. Electric fields, they are important in line formation, and people have measured them in the solar atmosphere, but not very much, and we won't talk further about them. Won't talk about molecules. We will talk about Stokes polarimetry, the way you interpret polarized line profiles, but the way you get from those observations in detail to what you want, the magnetic field in its orientation, too detailed to go into. We won't talk about X-rays, gamma rays. You'll hear about radio waves from Tim Bastian tomorrow morning. Helioseismology, a huge area that relies primarily on optical observations, but too much. Go into heliospheric imaging, but I'll come back in a second. Enough of this. So there are things that we're not going to talk about that you just can't ignore entirely, especially when they're so pretty. This is the Great Red Aurora of Remembrance Day or Veterans Day 2025. And you can see in the upper left, you have a red and a green aurora, aptly named. But this is the aurora from the ISS. And if you go to the NASA Scientific Visualization Studio website, you can actually see this as a movie. It's really pretty impressive. Here's another movie at the same time from Punch, which is for smallish satellites in sun-synchronous orbit, doing heliospheric imaging. So this is seeing the sun in polarized light, right, from Thomson scattering off electrons in the solar corona. It goes out to at least, I think, about halfway to the Earth in this wide field of view. And what you're seeing, besides, well, that's actually Venus. That's actually a comet. There are stars that have been suppressed, and of course the Milky Way. But what you see in the main action are these puffs coming out. Those are coronal mass ejections, and they're coming out nearly as what appears to be an expanding sphere because they're called halo ejections. These are ejections of mass that's toward the observer. So it goes out, forms a bubble, and as the bubble expands, if you're looking at it this way, you just see it expanding. So we're going to come back a little bit to the aurora for a reason. So what about this aurora, which is the pretty colors? Well, the theme of this today is when you do optical observations, one way or another, you often come back to spectroscopy of some kind, either narrowband or observing individual spectral lines. So the aurora is not just red and green. It's got a whole spectrum of things. It's primarily the red and green aurora. It's not my field. You'll hear more about it or have already. It's primarily due to neutral oxygen. And the only thing I want to draw your attention to is it's actually a pretty complex spectrum. We have neutral oxygen, we have some neutral nitrogen. Then we have this stuff. What's all this? This tells you the specific transitions behind the spectral lines. Some of you are completely familiar with it. Some of you maybe haven't had to deal with it. I'm going to go into it a little bit because if you deal with optical spectroscopy at all, you are going to run across it. And even if you don't need to master it in detail or remember it all, you're going to want to see it so it doesn't confuse the bejeebers out of you and keep you from focusing on what you want to learn about the process. And one more thing you'll see here is forbidden lines. Forbidden lines. What does that mean? Well, we'll come back to that a little bit. Okay, so the outline. What do we want to measure? We'll do this quick refresher for many of you on spectroscopic nomenclature, just so you know what to do with it and how to refresh your memory if you're going to need it. Polarization and the so-called Stokes parameters, the Zeeman effect, splitting of spectral lines in a magnetic field. Other effects in a magnetic field go by names, Hanle, magneto-optical, we'll get to that. Stokes analysis, which is where you come in data-driven. How do you take the data and turn it into what you want? And as another example, not on magnetic fields, but on the distribution of temperature. So you look at a piece of the sun, and there's some glowing plasma, and you say, well, what is it? Is it all one temperature? Is it two temperatures? Is it many temperatures? Well, how much of it is at what temperature? You want to know, because you want to relate that to how the atmosphere is heated and compare it with models. So you need an observational tool to tell you something about the distribution of temperature along some line of sight that you would like to model. All right, so what do we want to measure? All these things, and I won't go through them because many of them, particularly the bulk velocity, flows, and turbulent velocities, just not going to talk about too much. The main thing I want to leave you with is that everything you see there, all these properties, right, as they do in situ measurements. But now it's even harder because they vary in space and time, but you're not there. You're not in the middle of it. You typically have some line of sight through some amount of it, and it confuses you, confuses the situation. Can you take it apart? To what extent can you take it apart? But keep in mind, particularly the question of velocity field. It gets short shrift in what I'm going to say today, but it really complicates a lot of the models that we'll talk about, even though they're not that simple in themselves. Throw in an arbitrary turbulent velocity field and things get really messy really fast. All right, so this is really, for those of you who remember your introductory quantum mechanics, you can fall asleep. But it is necessary for just the nomenclature. Typically, all those spectral lines involve some quantum state of the atom or molecule, but we'll talk about atoms. And it involves the orbital angular momentum of valence electrons in the atom, and it involves the spin, the intrinsic angular momentum of electrons. And they can add together quantum mechanically in different ways. The short version of this is the only thing we're really going to talk about is the Russell-Saunders or LS coupling. It's where all the spins add together, all the spins of the active electrons, the valence electrons, add together according to quantum mechanical rules. All the angular momentum add together, so the little s's all add up into a big S, the little l's add up into a big L, and then you add L and S. And if you remember your textbooks or something, you'll see something about the this vector model, which I find to be just confusing because, yeah, they sort of add as vectors, but they add according to quantum principles. They can't just randomly orient them any way you want. The thing to take away is that your atom, when you're all done with it, you've got a total angular momentum, total orbital angular momentum L, and total spin angular momentum S, and they couple to form a total angular momentum of the atomic state. If the individual spins couple not to each other, but everything first couples to the nucleus, that's different, called JJ coupling. We won't talk about it. It does occasionally happen in solar physics and in heavy atoms where the nucleus is exerting its heavy influence. Okay, so all of that was to get to this point where you see this, and this is really what you know this much, right? You can go and figure all the rest out if you need to, which is it's a state that's got a total, an orbital angular momentum, a spin angular momentum. It added together to a total angular momentum, and this is called a parity state, which just has to do with whether the wave function is even or odd. All right? If you really want, if you look it up, and I'll get to this in a second because I want you to be able to go to where data are. If you look it up, you will see big, long things like this that tell you this is a transition. And you say, what the heck is that about? And how do I find out what I need? Like what its Zeeman sensitivity is, or this or that. And you have embedded in this what you typically will know. All the rest is giving you the configuration of all the electrons that are adding up to create this. So there's one on this side. This is what your upper level, and this is your bottom level. And if you really listed everything, it would be this big, long thing. And generally, you don't have to delve that far unless you go into the atomic physics of it. But this part, you're just going to want to be able to be comfortable with it and know where to go. Because if you even want to look something up, right? You go to one of these places like the NIST Atomic Database or Chianti. Who knows what the Chianti acronym refers to? Yes? Huh? Yes, it's not an acronym. I congratulate them for not making it an acronym. Now, of course, it really shouldn't be all capitalized then, but it's okay. Yes, and that is the wine country, Chianti. So both of these, but to look them up by lines and levels and things like that, you'll immediately get kind of lost if you don't at least have the familiarity at the level we just talked about in order to find what you want. Okay, so now let's go to polarization. This is all review, but polarization gets kind of tricky when you want to use it for scientific purposes and you're not just putting on sunglasses. So the usual way to express the electric field, right, with phasors and complex notation, right, you know how to do that. And so you have out here in the equation 4, the electric field is a function of time, right? You've got this propagator, right? That's the wave number and the frequency. That's the thing that makes an electric, a wave field. And then here, you've got the components of the electric field that's going to start oscillating the way it's going to do in space and in time. So that's this diagram, right? EX, EY, and then this is time, right? So if EX is something and EY is 0, it's just going to be a pure polarized electric field, and it's going to just do that. If EX and EY are the same, it's going to spiral around, and the spiral, if you project it on a plane, a given time is going to be a circle. If EX and EY are not the same, it's going to do this, but the projection is an ellipse, right? That's elliptical polarization, right? And so most of you are familiar with that, right? But it's not enough for what we want to do. We're going to be data-driven, and this isn't in situ that we're talking about, so you can't measure EX or EY, not anywhere. Got to have something way to use it. All right, so that's this. We need it to relate it to radiances, the strength of the light, not an electric field you can't measure, and sunlight is not completely polarized. Right? So if you ever see a description, and you'll see this in papers, where it talks about the Jones vector, that's a very elegant way to represent completely polarized light with a couple of complex components, blah, blah, blah. But in solar, although it can be useful, always got to remember there's also almost always an unpolarized component. All right, so there's the Stokes vector. There is Professor Stokes himself, looking very august, as people used to do. And here is its definition in terms of the time-averaged electric field. So I'm not going to dwell on this because it's important to know that there are Maxwell's equations behind all this, but it's not a direct measurement of these things that we use. For one thing, the frequencies are extremely high, right? These are optical waves, so you're not measuring EX or EY at any instant of time. They're all time averages. And that's one reason, but it is good to recognize that you don't have to use EX and EY. You could use any orthogonal basis, and they're all related by rotation transforms, and you'll see that with the Stokes vectors. Okay, so there's a book. It's very old, but it was very influential, and it's still a lucid presentation. It was influential way back when, in getting physicists to use Stokes vectors as a description of polarized light, and Shircliffe. And he specifically said, yeah, these are the definitions, but since you can't use it, it's more important to define it by how you measure it. And I won't go through it, but this is one example of how to measure the 4 Stokes components that completely characterize a partially polarized beam of light. And you have to make a measurement with a linear polarizer. You have to make a different measure with a linear polarizer that has its axis at a different angle. You have to make, but you have to have at least one that changes the phase between the two. Right? A linear polarizer just says, this measures how much, if you turn a polarizer this way, and then you look at it the other way, the way perpendicular to it, how much does it like this way more than that way? How much of the light comes through this way as opposed to that way? Preference. That's a preference for one sense of linear polarization. This is a preference for the opposite sense. But polarization is like this, so preference of this over this is not enough. You need another orthogonal component, and that is traditionally at 45 degrees, which is this over this. And this, you will see 2 times the angle in polarization all the time, and it's initially confusing as heck, but it comes back to that simple property of polarization. Its preferences of this and this does not tell you the preference of this over this, right? And you need a phase retarder. That's something that changes the phase between these 2 EX and EY so that it can change the ellipticity. Those are the Stokes vectors. IQUV is what used in astrophysics almost all the time. In many other fields, it's S1, 2, 3, 4 for Stokes. Okay. I wish I could spend more time on this because it's really great if you ever want to understand magnetographs. And those of you who go into this and go into seriously analyzing how magnetograms are made will quickly realize that you need to understand not necessarily the hardware if you're not designing them, but you have to understand what the components do because they don't do it perfectly. That's a big deal. It's hard to do these things quickly and fast. It's hard to do in space. It's even harder to do on the ground because everything is getting in your way and changing. So this is a way of representation, and Poincaré, he was a dude. Figured out everything, the 3-body problem, and he was a mathematician, impinged on physics in many ways, hugely influential. But you can represent the Stokes vector by something that has 3 spatial axes. So here it's S1, S2, S3. A state of polarization. Remember, you need 4 things for a state of polarization. Something on the surface of this sphere takes care of S1, S2, and S3. It characterizes it uniquely. But you also have the total radiance, and remember, it's partially polarized. So that means you have to make the radius of the point. You have to make a sphere into a ball. So if it's unpolarized, it sits at the center of the ball. as it becomes more and more polarized, it moves out radially to some place on that sphere. The use of it is, if I could reach up there, the action of a phase retarder is basically to rotate the sphere. And you can convince yourself that if you had something that rotated the phase, and you had complete control over the amount of phase that you change, and you could change which handle you use to rotate it, you can actually get from anywhere on the sphere to somewhere, let's say right here, in one motion. But you can't do it generally because we don't have hardware like that. The point of all this rotating and blah, blah, blah is the hardware takes you to a point where on the, where did I go? It takes you to a point which is represented by a point like this, and that means a polarizer. It's your analyzer. That's the last thing you see before the detector, and all the other rest stuff tells you how to get there. Okay, Zeeman effect. So here is Zeeman. Usually you see all the other pictures of these old stately-looking guys who'd already won their Nobel Prize. This is, Zeeman was the only one I could find looking young, confident, like you should all be, and supercilious, which maybe you should think about. As he did this work in his mid-20s. All right. Fundamental thing, and I won't dwell on the equations, but if an atom in a magnetic field can acquire a potential energy because, unless it has zero total angular momentum, right, it acts as a magnetic dipole. You can think of it, there's some residual, and in a classical sense, this orbital cloud of electrons is like a current. You put a current in a magnetic field, right, and it experiences a torque. So what happens in a magnetic field is you've got the atom, here's a magnetic field, the atom has some angular momentum. It's not really spinning, that's quantum mechanics, but we'll think it's spinning. That's how they thought of it when they figured this stuff out. It's spinning, it's got a magnetic field, it exerts a torque. What does it do? It does this, like a top spinning in a gravitational field. It spins around, so there's a torque, and also there is a potential energy. You've got to conserve angular momentum, so there's a potential energy associated with that. And that change is mu dot B, where mu is the magnetic moment. And the magnetic moment, this is why I went through the L and the S and all that jazz, the magnetic moment in LS coupling is given by this simple formula. And then there's one more thing you'll need, won't go into it, but you'll see it all the time. It's the Landé G factor, right? Because L and S is not enough. You got to know how sensitive the atom is to a magnetic field. Some of them are virtually insensitive. Some of them are much more sensitive, and those are the ones we're usually interested in. That's the Landé G factor, and you can see it's got L, S, and J, okay? This is all by way of introduction. By the way, this is one of Zeeman's pictures where the two sodium D lines, which are at about 580 nanometers in the laboratory, were split. So there's a Nobel Prize. I will not go into, but you've heard of, selection rules, right? In quantum mechanics, not everything that can happen does happen under certain circumstances. So there are a whole bunch of rules about what can happen between the bottom and the top, and you won't generally have to worry about that, because if you're using data from it, it's because it's at some level a permitted transition. But I will draw your attention to the forbidden part again, the forbidden part. Taste it, but be cautious. Don't be too young and impetuous. These so-called forbidden lines are lines that, spectral lines that in a dense environment, you just don't ever see. That makes them in some sense useful, because in a dense environment, you don't ever see them, because they are lines where if you excite something to a level, it doesn't want to come back down again. It just sits there. And so it could do this, but it doesn't want to, right? And usually what happens in a dense plasma is some other atom comes along and collisionally de-excites it. Collisionally de-excites it. There's no photon, there's no line. But in the solar corona and in the upper reaches of the Earth's atmosphere, these lines matter, and they're very useful. There's the red and the green aurora that comes from forbidden lines of oxygen. So the rules say they can't happen, means they happen much less often and only in not too dense plasmas. And also in the solar corona, this is during an eclipse. So you will see a lot of, this is one reason that ground-based eclipses are still very important. These data are not old, and they're still doing this. This compares iron 10, 11, and 12. These are ionization states of iron, and this is a way to make temperature maps of the solar corona using forbidden lines. So all you really need to know is that forbidden lines, all that background, they're a different breed of cat. And if you study these kind of data, you will need to know at least enough about them to understand that forbidden lines work differently than the other kind. All right, let's not go into the Zeeman components, but except to say that the simplest Zeeman pattern, and the one that you will often see and are often used in real-world examples that you might deal with, are the spin zero, the total spin zero triplet states. So you see one line in a magnetic field, it can split into three. There are certainly ways that there are more complex patterns. And sodium D, for example, over on the right is more complex, and sodium D is a valuable line to be used in solar physics analysis. The key thing about the Zeeman splitting, at least in the simplest case, is that it matters. What you see depends on your line of sight compared to the magnetic field, right? If you are looking along the magnetic field in a simple Zeeman splitting, you see, remember, it's split because there's an energy perturbation of this dipole in a magnetic field. So there's an energy separation, but you see only a left circular and a right circular polarization. You see two lines. If you look perpendicular to the magnetic field, you see two linearly polarized components, and then another linearly polarized component at the rest wavelength. If you see an intermediate angle, you see a combination of those things. And this is just an example of what it looks like in a real spectrum. And every time I show you a real spectrum, appreciate that if you were analyzing these data, it never looks as simple as that. It never does. So this is just to show you a more confusogram and bring in the matter of noise, all right? This is from spectra from Hinode, and it's the same little piece of the sun with increasing exposure here. And it shows the zoo of profiles you can get, and some of them get pretty darn complicated. And I'll tell you right now, they are not explained by almost anything I'm going to say, because the kind of complex software that you would use to try to interpret this, right, is not what can be talked about in one lecture. So, but it's important to know what the simpler things can do so you know when you need something more. It also gives you an idea that when you have substantial noise, as you often do, it really gets messy, because none of these formalisms, unless you take special care or do Monte Carlo simulations, is going to account for what noise is going to do. The Hanley effect, we're back to the distinguished looking guys. The Hanley effect, so we have talked about the Zeeman effect. The Hanley effect is one of the things of scattering polarization. A magnetic scattering, right, is linear polarization caused by coherent scattering of anisotropic radiation. So if you put an atom in a uniform radiation field, scattering is when you don't very much change the energy. You excite something, it de-excites, sends the photon at nearly the same frequency right out again, right? It can change its frequency a little bit, but it's not a excitation to another level and then excitation followed by some other completely different wavelength. It's coming back to the same place. That's scattering. It's coherent because of that reason. But if it's in an isotropic radiation field, you can't polarize unpolarized light, because how would you? If there's no magnetic field and there's no polarization coming in, there's no direction. It's spherically symmetric, there's nothing you can do to it. All right, if you have an anisotropic radiation field, you've defined a direction, and your scattering can now be anisotropic. If you now add a magnetic field, you got two things, two directions. You've got an anisotropy that has a preferred direction. You've got a magnetic field that has, in general, a different direction. What would you guess about what's going to happen with a magnetic field and something else? Yep. Every time you come to these phenomena, think of precession of something around something, and you'll get at least a heuristic feel for what's going on. In detail, the Hanley effect. So the Hanley effect is scattering polarization with the addition of a magnetic field that changes the nature of that scattering. It changes its directionality, and it can also change its sense of polarization. The takeaway is it operates in an area which is at weaker field strengths than you can typically measure with the Zeeman effect. But it's trickier. But it can and has been used to measure magnetic fields in the corona and in prominence, for example, down at the level of 5 or 10 Gauss. Quite weak fields that you generally cannot measure with the Zeeman effect. The only thing I'll say about it in terms of what it is and why it operates in a certain range is this. Remember that there are these Zeeman split levels. If these levels are not very far split, in fact, they are split by less than the natural line width. The natural line width, remember, is something that's determined by the lifetime of the state, right? It's the uncertainty principle. Since delta t is finite, you have to have some line width. If they're really close, then their quantum states interfere. That's the region of the Hanley effect. As the field gets stronger, the Zeeman sublevels are split enough that they don't much care about each other, and the Hanley effect loses much of its diagnostic power. I think I'm going to essentially skip over this. It may be that tomorrow you'll hear something about the Faraday effect important in radio waves. But these are the difference is that the Hanley effect is a local effect. It affects a photon impinging on an atom and being scattered. Magneto-optical effects refer to an electromagnetic wave as it travels through a medium. So it matters how far you've traveled, right? It's cumulative. The Hanley effect is a point effect. And if you ever go in this direction, and if you don't get this book. It has all the gory details. The point is, now finally I'm going to make some contact with at least what data could look like. And the only thing I want to point is here. Here is you. You're the observer. You're looking this way. You've got a magnetic field, and the magnetic field has an inclination to your line of sight, and it has an azimuth around this direction. That's all you need to know about the coordinate system, right? And you can make a model of what you should see for a light coming through a stellar atmosphere, in this case the sun's atmosphere, in the presence of a magnetic field with some pretty restrictive assumptions on that atmosphere you're going through. And those of you who know about, I've talked about Milne-Eddington models, and most of the software you use is going to be Milne-Eddington. It's actually a very restrictive atmospheric model, but it's useful as well. So these are what Stokes profiles look like. All right, so this is a spectral line. And we are going to introduce Zeeman splitting. Remember, it literally splits into two different wavelengths with different polarizations, or right and left circular polarization. So what happens is you take one and you split this into two, and you give it one sign, and take one and shift that line pole a little bit this way and give it the opposite sign. It basically acts like a derivative, and that's what you get. This is, this one. This is Stokes V. It's a classical Stokes V profile, and remember, we saw that schematic where you had two on the outside and one in the center? That's Stokes Q and Stokes U. And the ratio between these two and whether the peaks go up and down, that depends on that other angle going around, right? Here's your this, you've got an inclination of your magnetic field, and you've also got this azimuth. It's confusing, but it's not when you remember one thing. Q and U are just related by a rotation transformation. And you'll see that. And so a lot of times when you can, you construct a coordinate system so that one of them is 0. So there's a strong line, a weak line, and weak splitting. Weak splitting, by the way, when you see that and you're analyzing, you're reading about magnetograms and things like that, doesn't mean weak in an atomic sense. It's confusing. Almost all of the splitting is weak in the atomic sense. It's not what we call the Paschen-Bach effect, where LS coupling has to be thrown away. This means that the splitting is weak compared to the line width. And what is the line width? It's not what's called the natural line width, not in the sun, because in the sun it's mainly controlled by what? The Doppler width. That's the width, the red and blue shifts caused by the atoms, and increases as the square root of temperature, right? KT over M. So if we go to a strong line and strong splitting, here's what I want to show you. Well, this is what you expect. This is the intensity profile. See, it split the lines completely apart. You expect what you expect in this circular polarization signal, right? If it's longitudinal, it means along the line of sight. And you say, wait a minute, I see Q and I see U. I see U. Never mind. Yeah, these are confusing plots because these are very, very small and you can't read it. Come back to that, because to help you, you should do something different. The only other thing I want to talk about here is that if you're transverse to the line of sight, that's where normally you see, remember that few slides back, you look purely transverse, you see these linearly polarized components. But if you have a very strong field and you include these magneto-optical effects, all this junk that we said, given you a flavor for, but it's hard to incorporate it. But if you see something like this, see that, where it goes below and above? That can never happen without those effects. So they are real things that show up in models and they show up in observations. Here's another example of a magneto-optical effect. You saw this, where it does this. This is a line where these are theoretical profiles of the Stokes U parameter in a coordinate system where it should be 0. But, in fact, it's not 0. And in observations, you can sometimes see it and measure it. So the simplest view of how you form the emergent radiation from light passing through a magnetic field is not enough to account for observations. Not even observations that were taken 30 years ago. My point is, if you want to, but you need to know that those things are present so that when you add the complications of real model atmospheres that you will use, velocity fields, turbulence, you're going to want to know what you see even without those things. One way to get a sense for it, I did put this here so you would read it. I would put it here so it's actually a very simple set. If the splitting is quite weak, a lot of things go away, including the magneto-optical effect, the Hanle effect. It's not that they go away, it's that they're so weak you'll never see them. And then everything becomes rather simple. And you can Clyde code this up in 5 minutes. Or you can, anyway. Now, unfortunately, I can't show it to you the way I wanted to, but I coded it in Mathematica. And this shows all the parameters that go into it. You see this azimuth, this inclination and azimuth, right? This and this, always got to have that. These other things have to do with this Milne-Addington atmosphere, how thick it is, and blah, blah, blah. This is how strong the line is compared to the continuum, right? Eta 1 is a weak line. Eta equals 7. Never mind the parameterization. It goes up, it means it's a stronger line. Okay, and since I can't, oh well, if I get it back, I'll show it to you. Anyway, I animated this, but I couldn't, or put some nice sliders on it. But if you do it, you can put some sliders on it, and you'll see it's much easier than trying to look at a whole bunch of figures. Don't do it. Code it up, look at it, and you'll get a three-dimensional sense of what happens with these parameters. Okay, so what is now the meat of it, right? So we're ready to roll. We'll analyze Stokes profile data. Yes, well, if only. Here's, as is known in Greek mythology. All right, so you're going to need all the stuff I talked about. Then, where am I in time, by the way? Good. Thank you. You're going to need all that, at least an awareness of this stuff from that messy formalism. But you would be working with a real model atmosphere, probably not a Milne-Addington atmosphere, which is highly simplified. You would get it probably from a radiative MHD simulation that had a chromosphere and a corona, if you could get it, right? And had velocity fields, and probably turbulent velocity fields. You're going to then have to have a polarized radiative transfer code, or your tool is going to have to use that, and you're going to want to know what it did and what it didn't do, right? Is it, well, it must be non-LTE. It's not in the local thermodynamic equilibrium. Almost no one will use that anymore. It has to handle polarized radiation. It'd be nice if it were three-dimensional. There are many codes out there now, but they're computationally intensive. It's scattering. So scattering, it does change the frequency a little bit. Exactly how does it do it? That matters. That's partial frequency redistribution. Then you're going to want to know how it was measured. Observations. That's, what did you do with those polarizers and wave plates? What order did you do it in, and what was their orientation, and why? Why do you even care about that as, let's say, a data analyst and you want to assimilate this stuff? Because polarizers are not perfect. Retarders, the phase changers, are not perfect. You don't know their axis with perfect. You don't know how much they retard to phase. They have errors, and they may be time dependent. All those things, and you need to know the modulation scheme. That's the lingo for all those polarized changers and analyzers you put in the beam to figure it out. And this is a real world thing. I mean, there was a problem with the heliospheric and magnetic imager on SDO. It's the thing that makes those full disk magnetograms. It's called the 24-hour effect. And it's been around for 15 years. And people still don't know exactly how to get rid of it. They know it's instrumental, but they can't get rid of it completely. So there's that modulation scheme. You have to at least know what's going on. And then there's the inversion code. Everything that Farzad talked about, particularized to this problem. And I try to give references to, recent things so you can know what the state of the art is in inversion codes and things like that. So, this is just a basis for further investigation if you want to go in that direction. Have to race through this, and so I'll just be very restrictive in one thing. One thing about the Zeeman effect, these are observations at an iron line at just over 1 micron. Now, why would you go to longer wavelengths with the Zeeman effect? Because in weak Zeeman splitting, it's pretty easy to show that the circularly polarized signal, because it's antisymmetric, increases in magnitude as the square of wavelength. So going out to longer wavelengths, right, if you go from 500 nanometers to a micron, and your magnetic sensitivity of the line, that's that G factor, is the same, you get 4 times more splitting. So these are really very, very beautiful data from DKIST, the Inouye-based 4-meter telescope, showing a measurement, convincing measurement of coronal magnetic field at, what is that? 16 Gauss. No way that could be done successfully before DKIST, and no way it could be done at visible wavelengths. So things are, really exciting things are happening in measuring the coronal magnetic field directly, which for those of you who are interested in the other things, right, the coronal magnetic field, knowing that and being able to extrapolate it to a place away from the sun where it acts as a so-called source surface to produce the heliospheric magnetic field. It all starts here. You need to get out to there so that you can then make models that go out into the heliosphere. And it's been very hard to get that boundary condition because you can't measure magnetic fields close to where you want to set your boundary. So this is making real progress in that direction. One cautionary tale, and this is the same data, these are those circular polarization measurements. They look a little ratty, but they're really spectacular. And this is how it looks. But then they modeled it. Here's the model. Here are the data. And I think they said something like, it bears some resemblance. And that is the state, I would say, of the art in modeling at this point. I think I will skip over this, but if you want to go into it, this reference will show the state of the art in trying to identify these other effects, the Hanley effect in particular, in scattering polarization. And this is done from a rocket experiment in magnesium lines. They're called the H and K lines of ionized magnesium. The CLASP rocket measured them in the vacuum ultraviolet. So we at least go extreme ultraviolet to infrared radio. We'll leave for tomorrow. Now when you get to magnetograms, the thing to know about them is it often introduces what are called magnetograms. So now we're not just measuring, putting a spectrograph slit necessarily and seeing lines being split. We're trying to measure the magnetic field over the way you normally want it, right, over 2 dimensions. You can do that by stepping a spectrograph slit, and that's a lovely way to do it, especially if you're a spectroscopist, but it's slow. And what you really want is a 3-dimensional detector. You want to measure 2 spatial dimensions and wavelength at the same time, an energy resolving detector. And they sort of exist, but not in a practical way. By the time you're middle-aged, they might. That would be good. But so in order to do this, instead of using a spectrograph slit, you typically use very narrow filters, right? So Here's an example from the heliospheric and magnetic imager on SDO. All right, these are all these are passbands, so you're sampling the spectral line. So it's like a very coarse spectrometer. All right. The main thing about them is that you need to know that these need to be calibrated, and they are tricky because these passbands have to be known very exactly. You have to know whether they vary, whether they're temperature dependent, whether they're angle dependent, and all sorts of stuff. They will show up in your data. All right. But these full disk magnetograms, which are almost always done with these filters, are very important. Right? And I think you already know that they're important for solar cycle studies. They show you the total magnetic flux. They are the ones that are used to extrapolate out to the so-called source surface and make all your models for the heliospheric magnetic field that many of you want to use, right, in space weather or its effect on the magnetosphere and so on. The only thing I'll say about that is the 0 point of the flux of these things is very important. A fraction of a Gauss uncertainty in the 0 point, which is between the green and the yellow there, the outward going magnetic field on average and the inward pointing magnetic field, can make a difference to a solar cycle prediction and to the coronal magnetic fields. In order to show you anything, these are spectacular data. This is the state of the art, which is, where is it here? Let's look right here. You can actually see emergence of magnetic field at the subarc second level. And this is opening up a whole new, and a lot of these other things are showing like why you never see it at these lower resolutions that we've had before, like at the resolution of the magnetogram you saw in the previous slide, only with these observations. And these are what you can couple to state-of-the-art MHD simulations. There's a lot of exciting work there. But these things in and of themselves are not, in terms of data-driven, there's a lot to know about these. They're often taken with adaptive optics, and there's a lot of instrumental effects that come with that. I'm going to skip this. This is just to say that even the continuum light, we've talked about the Zeeman effect and all the atoms and blah, 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 but even the continuum light between the spectral lines is actually polarized. And near the limb, the spectrum looks rather different. Some people call it the second solar spectrum. It's this linearly polarized second spectrum. You can measure it, and you can compare it with models. So I'll just do the takeaway. Photospheric continuum polarization is small, but it's not negligible, it's measurable, and it is an independent diagnostic of some power. And you need to know it because it's there if you're trying to measure the polarization of a line, including with the Hanle effect or the Zeeman effect or whatever it is. There's some polarization there of that continuum that if you don't include, you will not get the correct answer from your Stokes profiles. And yeah, okay, it's about 0.1%, 5 arc seconds off to the limb. But for those of you who know the precision that Stokes profiles are often measured at, which is at 0.01%, it's not. Okay, so I want to at least touch on this, the differential emission measure. I want you to be able to interpret one of these, which has the log of temperature against something called the differential emission measure with the silly units of, meters -5 per Kelvin. And what you see is a curve and then a bunch of lines, spectral lines. So what does that mean? Right? The takeaway is that this is the most common diagnostic for understanding along a given line of sight the relative amount of gas at different temperatures. How much of the volume that you're looking through is occupied by 1,000,000-degree gas versus 500,000 degrees versus 3,000,000 degrees. What is its temperature structure? One thing to know about the differential emission measure, called differential because it discriminates among the temperatures, is that it's only defined in an optically thin plasma. This is the definition of it, right? And the key thing here is H is along the line of sight. So the way to decode this is it depends on the number of electrons and number of protons because, or the number of hydrogen atoms, because the DEM, differential emission measure, is really only defined for collisional processes. But that is mostly what happens. In all these pictures you see from the Solar Dynamics Observatory, all these pictures at the different wavelengths, those are all collisionally excited spectral lines, and you can use them for differential emission measure. So the HDT, that's its way of saying how much of that along the line of sight, if you will, bunch of little cubes along that line of sight, how much of that is occupied by each temperature, right? Is it all cold? Is 50% of it hot? And so on. How do you relate that to radiance? Radiance is what you measure. Basically, the radiance that you're going to measure has to do with the temperature distribution, because the light produced by a cubic centimeter of stuff, right, depends on what's in it, which atoms are in it. That's this. That's the so-called abundance. What is the abundance of every atom? Right? Because a spectral line is produced by some atom, how many of them are there? How much is there at that temperature? And then this thing called the contribution function is all the atomic gore, right? If you know how many 5 times ionized oxygen ions there are at a given temperature, you still don't know how much light that's going to make. You need the atomic calculations. Normally, you will not be doing that. You will rather be looking it up, right? And the contribution function is a function of temperature and density and the ionization fraction, right? Gotcha. So if you want to know how much oxygen 6, that's 5 times ionized oxygen, that produces a very useful extreme ultraviolet line that's used in these differential emission measure, DEM analyses, right? But you've got to know at a given temperature and a given density of oxygen, how much of it is 5 times ionized, right? Got to know that. So you have to do an ionization calculation. That's how many you've got that are ready to give you the line you want. Then you have to know how strong that line is. The point is, it's all buried in the contribution function. You go to Chianti and you let them do it for you, as long as you recognize the assumptions that are made. And they are quite a few, and if you are going into the state of the art, you're going to have to know what those assumptions are and whether you are going to need to think about relaxing them, and if so, do you know how? So each spectral line, so here's a Hanode spectrum. See all these spectrum lines? These are all the ones where you might want to use them as a temperature indicator. Why? Because each spectral line of iron 12, all right? Well, you only get iron 12 in a certain range of temperatures because if it's colder, you get almost no iron 12. It's not hot enough to get that high ionization. Or if it's really too hot, then it's going to be mostly iron 21 or something. So each spectral line, look at them all, it has a so-called contribution function. Those are the temperatures that that line helps indicate, right? That's a logarithmic scale, by the way, so those aren't as coarse as they may seem. It's logarithmic here. So these are all, right? And now you can, in fact, interpret, oh, great, why has it come to the very end? Help me there, get back to where I need to be. Hello? I'm not missing slides. I was just about to advance a slide and it went to the end. I want to go backward. All right. All right, I got it now. Thank you. You can now interpret this, which is showing all these spectral lines. In your mind, you're reminding yourself that they each really have a contribution function. They're not point indicators of temperature. This is where they peak. And they're the ones telling you, that spectral line, by how bright it is telling you how much gas at that temperature there is along the line of sight, compared to another line that's telling you how much gas there is at a different temperature. Okay? So you know now how to interpret it with spectral lines. I will skip over the fact of, because I think it's conceptually relatively straightforward, right? Often you don't have these spectral lines. Instead, you have filter bandpasses, right? As they do in the atmospheric imaging assembly on SDO that many of you have seen, the EUV image of the sun in the 194 angstrom bandpass. Well, that's really a filter. There's more than one spectral line in there. So you got to know what spectral lines are in there. You've got to use a model to deconvolve, to take the filter response and multiply it by the spikes of the spectral line, okay? But it's conceptually straightforward. And now we get finally to what Farzad was talking about, which is we have passed over the fact that this is what you want, and it's an integral equation. Okay? So lots of approaches to this. I've tried to give you references here to some very recent ones using machine learning and AI to help do this inversion. Something that is more straightforward but is still useful is illustrated up here, where they use, never mind all this stuff up here, that's the way to get an initial estimate, but it's a way to get to invert what you observe, which are the radiances through a bunch of filters, right, into this differential emission measure and have error estimates or uncertainties in your reconstruction. In the lower right there is an example of an AI-assisted thing. You'll notice what you see is two temperatures, right? So it's comparing two temperatures, and you're seeing a map, right? Because in olden times, people would say, what's the differential emission measure of a typical quiet region or a typical active region or a typical bright point? That's not enough anymore. You want to know the differential emission measure in a two-dimensional array, right? So here's an example of that from 2019. And you are seeing those are different temperatures, and it's showing, right, how much a given region, you have essentially a differential emission measure at every point in the field. Now, what you really want is to wander through that with VR glasses, right? Because then it's really a data cube, and you want to kind of wander through it. And just as the final stage of refinement, and this is work that was done some time ago by including Farzad, remember that you are looking through, it's defined for this path through an optically thin medium. Right? So you don't know anything about how it's arranged in there. Here's a hot one, here's a cool piece, here's a hot piece. You could arrange that any way you want because you get the same output. But what if you would like to know, is the hot stuff really, this is your line of sight. Is the hot stuff here? And it's cooler here? Or is the hot stuff in little blobs? You want it three-dimensional. Well, you can imagine, you cannot do that with one line of sight, right? Because you can't take it apart. If you have multiple lines of sight intersecting that column in different directions, then maybe you can take that apart. The answer is it can and has been done. It's an even more difficult inversion problem, but this is an example from this paper of different regions that have different emission measures, different regions and different radii, right? You can at least take a region and probe its temperature structure as a function of height, which you cannot do with a single line of sight because the height dimension, or whatever the dimension is along your line of sight, gets collapsed. And I will not do this, but for those of you who are interested, this is still your friend. This, if you want to know, if you go into a paper, this, for example, is from the Phi instrument on Solar Orbiter. And it uses these modulators, a liquid crystal wave plate 1, liquid crystal wave plate 2, and a polarizer. That's how the Stokes parameters are. If you are assimilating that data, you will need to know at least, not the mechanics of it, but A, how those things work in terms of their uncertainties and their temperature dependence. Particularly liquid crystals are almost always temperature dependent. And the way you can do that, at least to understand it qualitatively, right? All right, get the direction right. There are only two of them. Is if you want to know, when the temperature, what if the temperature is uncertain by 2 degrees? And with some difficulty, either in the paper or by contacting, and as data analysts, you may sometimes have to contact people associated with the instrument and say, I want to put in an uncertainty. The temperature is uncertain by this much at the time of observation. What does that do to the retardation of liquid crystal 1? And they say, oh, it could be wrong by 3 degrees. And so you can reach into your Stokes sphere, your Poincaré sphere, right? And you were saying, well, what does that do to what I thought was circular polarization? Circular polarization would be up here at the pole, right? And normally this quarter wave plate is going to take that down to be analyzed at the equator. But it's not doing that. It's taking it there, a little short or a little far. And that gives you a feeling immediately how much the error might be. And in fact, you can calculate it. And you don't calculate it by using the sphere or anything, but this tells you what type of errors you are going to introduce. And as a data analyst, what you have to be worried about. Okay. Thank you.
Hey, questions for Doug?
I've confused them.
Covered everything.
I have a challenge for you, though.
Oh, yeah.
So I couldn't get this Mathematica simulation, but it's a trivial thing to do. This was the weak field approximation, right? And so I coded up with some sliders here. So instead of looking at a bunch of pictures, right? You just code it up this way, and you can see the full range as you change either the inclination of the magnetic field or the azimuth, right? You can see how the Stokes profiles change. And
fantastic.
If you do this quickly, if you do this with yourself,
show it again, because it's now on the screen.
Pardon?
Show it again, because they can now see it.
And you can, of course, if you animate it, you can do both at once, but that, to me, became immensely confusing and also did not serve the purpose of understanding in my head what azimuth does and inclination. The inclination is more informative because, say, the azimuth is really just a rotation transformation between these two guys, and so these quasi-sinusoids just kind of play off against each other. So my challenge to you is, if any of you are interested in, this is weak splitting. That's that slide that you can have Claude code you up in 10 minutes or something. I can't get Claude to do that. You can. But the equations that you can find in that thick book, but also in a lot of papers, which does include the magneto-optical effect, the Hanley effect, and for the Milne netting in the atmosphere. So it's actually what a lot of your current data analysis software uses, right? Your fast inverters that I heard talk about yesterday, those are almost exclusively Milne-Eddington. Code that up, and you can do the same sort of thing to see where magneto-optical and these more subtle effects come in. It's not in this simulation. This simulation tells you what the gross thing does, and that can tell you what these more refined things do. And that gives you the background that when you mess things up even further, as you surely will by putting in velocity fields and all that, at least you'll know what you're messing up.
Yeah, hi. I have a couple of questions. So, first would be like I was thinking, like these polarization measurements, Will they help us in distinguishing between the wave-driven and magnetic reconnection-driven energy release processes in corona? Like, do these measurements help us in that direction?
I think they can. You have, first of all, velocity signatures, potentially of wave heating, right? Direct velocity signatures. People have searched for them, and there's certainly a lot in the literature that claims you can see. And you can certainly see oscillations of Doppler velocity now that people have attributed to I think mainly slow mode waves. I don't know, and somebody needs to correct me. I'm not sure there have been any that we've used direct Zeeman techniques, for example, to see Alfvén waves. So I think the answer is yes, and there's some, and I have to be very careful because I'm too ignorant of some of the literature. But it's not, well, I can say this, it's not very definitive because people still argue about it incessantly, okay. Right? And another feature of doing that is to get increased angular resolution. Because if you want to see, to use discriminations, and one of them is possibly through the differential emission measure, right? Because if you look at nanoflare kind of heating, that tends to, because it's a nanoflare, there's a reconnection event, and it creates extremely hot, maybe 8-10 million degree plasma very quickly, yeah. But it also cools very quickly by the nature of the radiative cooling rate, right? And so you need, but those regions are very small. So they get all washed out. So one of the things we like to do very much is have a very high angular resolution. So think of HMI, but with a 1/10 of an arc second resolution to see spikes in temperature, which you would not so much see with wave heating, but with wave heating you could see oscillating signals in temperature and then potentially in other diagnostics.
And if I got that right, like these forbidden lines, these are ideal for coronal magnetic field diagnostics?
Say again now, please.
If I got that right from your presentation, like these forbidden lines that you mentioned, are these ideal for the coronal magnetic field diagnostics?
Sorry, just didn't get it.
Yeah, the forbidden lines, which you were, forbidden lines.
Oh, the forbidden lines,
Yeah.
yes. I'm sorry.
Okay.
My problem.
Are these ideal for coronal magnetic field diagnostics, if I got that right?
Oh, yes, definitely.
So, to what extent do the line of sight integration that limit the accuracy of their measurement?
They absolutely confusion along the line of sight is an issue. They are, and it is with like those. Remember, I showed the thing that was I thought was very impressive, measuring like 16 Gauss.
Yeah.
Right, which is for our Zeeman effect is quite weak. Excellent measurement. First of all, it is a forbidden line. That is a forbidden line. So you could not, there are essentially no permitted lines in the corona where you can measure. But by the same token, the line of sight confusion is definitely there. And as far as I know, without multiple lines of sight or rotation, assuming things don't change much, you can't take that apart.
Okay, thank you.
let's thank Doug again.
Thanks.
So